now beginning serious development of BFR. So you can see that the payload difference is quite dramatic. BFR in fully reusable configuration, without any orbital refueling, we expect to have a payload capability of 150 tons to low Earth orbit. So, and that compares to about 30 for Falcon Heavy, which is partially reusable. Where this really makes a tremendous difference is in the cost, which I'll come to in some of the later slides. So let's go to the next slide. And by the way, so with BFR, you can get a sense of scale by looking at the tiny person there. It's really quite a big vehicle. Main body diameter is about 9 meters or 30 feet. And it consists of the booster is lifted by 31 Raptor engines that produce a thrust of about 5,400 tons, lifting a 4,400 ton vehicle straight up. So then, just the basics about the ship: 48-meter length, dry mass we're expecting to be about 85 tons. I mean, technically, our design says 75 tons, but inevitably there's mass growth. And that ship will contain 1,100 tons of propellant with a design of an ascent design of 150 tons and a return mass of 50. So you can think of this as essentially combining the upper stage of the rocket with Dragon. It's like your Falcon 9 upper stage and Dragon were combined. So as I'll go into each of these items in detail, but you've got obviously the engine section in the rear, the propellant tanks in the middle, and then a large payload bay in the front. And that payload bay is actually 8 stories tall. In fact, you can fit a whole stack of Falcon 1 rockets in the payload bay. Compared to the design I showed last time, you'll see that there is a small delta wing at the back of the rocket. The reason for that is in order to expand the mission envelope of the BFR spaceship. Depending on whether you're landing or you're entering a planet or a moon that has no atmosphere, a thin atmosphere, or a dense atmosphere, and depending on whether you're re-entering with no payload in the front, a small payload, or a heavy payload, you have to balance the rocket out as it's coming in. And so the delta wing at the back, which also includes a split flap for pitch and roll control, allows us to control the pitch angle despite having a wide range of payloads in the nose and a wide range of atmospheric densities. So we try to avoid having the delta wing, but it was necessary in order to generalize the capability of the spaceship such that it could land anywhere in the solar system. So let's look at a couple of things in detail. So the cargo area has a pressurized volume of 825 cubic meters. This also is greater than the pressurized area of an A380. So really is capable of carrying a tremendous amount of payload. In a Mars transit configuration, since you'd be taking 3 months in a really good scenario, but maybe as much as 6 months, some number of months, single-digit months, you probably want a cabin, not just a seat. So the Mars transit configuration consists of 40 cabins, and it sort of depends on, you could conceivably have 5 or 6 people per cabin if you really want to cram people in. But I think mostly we would expect to see 2 to 3 people per cabin. And so normally about 100 people per flight to Mars. And then there's a central storage area, galley, and a solar storm shelter, entertainment area, and I think probably a good situation for at least BFR version 1. Then going to the main body of the vehicle, the center body area. This is where the propellant is located. And this is subcooled methane and oxygen. So as you chill the methane and oxygen below its liquid point, you get a fairly meaningful density increase. You get on the order of 10 to 12% density increase, which makes quite a big difference for the propellant load. So we're expecting to carry 240 tons of CH4 and 860 tons of oxygen. In the fuel tank are header tanks. So when you come in for a landing, your orientation may change quite significantly, so you can't have the propellant just slushing around all over in the main tanks. You have to have the header tanks that can feed the main engines with precision. So that's what you see immersed in the fuel tank. Then the engine section. So the ship engine section consists of four vacuum Raptor engines and 2 sea-level engines. So all 6 engines are capable of gimbaling. The engines with the high expansion ratio have a relatively smaller gimbal area or gimbal range and a slower gimbal rate. The 2 center engines have a very high gimbal range and can gimbal very quickly. And you can land the ship with either one of the 2 center engines. So when you come in for a landing, it will light both engines, but if one of the center engines fails at any point, it will be able to land successfully with the other engine. And then within each engine, there's a great deal of redundancy. So we want the landing risk to be as close to 0 as possible. And then some basic stats about the engines. The sea-level engines are about a 330 ISP at sea level. The upper stage engine is 375. Now, this is version 1. So I think over time, there's potential to increase that specific impulse by 5 to 10 seconds. And as I was mentioning, also increase the chamber pressure by 50 bar or so. And then for refilling, where you just saw the 2 ships would actually mate at the rear section. They would use the same mating interface that they used to connect to the booster on liftoff. So we'd reuse that mating interface and reuse the propellant fill lines that are used when the booster is, when the ship is on the booster. And then to transfer propellant, it becomes very simple. Use control thrusters to accelerate in the direction that you want to empty. So, if you accelerate in this direction, propellant goes that way, and you transfer the propellant very easily into from the tanker to the ship. So going to rocket capability. This gives you sort of a rough sense of rocket capability, starting off at the low end with the Falcon 1 at a half ton, and then going up to BFR at 150. So I think it's important to note that the BFR has more capability than Saturn V, even with full reusability. But here's the really important fundamental point. Let's look at the launch cost. The order reverses. Now, at first glance, this may seem ridiculous, but it's not. The same is true of aircraft. If you bought, say, a small single-engine turboprop aircraft, that would be $1.5 to $2 million. To charter a 747 from California to Australia is $500,000, there and back. The single-engine turboprop can't even get to Australia. So a fully reusable system, a fully reusable giant aircraft like a 747 costs a third as much as an expendable tiny aircraft. In one case, you have to build an entire aircraft. In the other case, you just have to refuel something. So it's really crazy that we build these sophisticated rockets and then crash them every time we fly. This is mad. Yeah, I can't emphasize how profound this is and how important reusability is. And often I'll be told, but you could get more payload if you made it expendable. I say, yes, you could also get more payload from an aircraft if you got rid of the landing gear and the flaps and just parachute it out when you got to your destination. But that would be crazy, and you would sell 0 aircraft. So reusability is absolutely fundamental. Now I want to talk about the value of orbital refilling. This is also extremely important. So if you just fly BFR to orbit and don't do any refilling, it's pretty good. You'll get 150 tons to low Earth orbit and have no fuel to go anywhere else. However, if you send up tankers and refill in orbit, you can refill the tanks all the way to the top and get 150 tons all the way to Mars. And if the tanker has high reuse capability, then you're just paying for the cost of propellant. And the cost of oxygen is extremely low, and the cost of methane is extremely low. So if that's all you're dealing with, the cost of refilling your spaceship on orbit is tiny, and you can get 150 tons all the way to Mars. So automated rendezvous and docking and refilling, absolutely fundamental.